All right. So 16D is the standard normal distribution. So Carl Friedrich Gauss was a German physicist and mathematician who was alive from the year 1777 to 1855. The standard normal distribution is sometimes called the Gaussian distribution and is in the shape of a bell curve. So that kind of curve that you can see over there on the right-hand side. The graph of the standard normal distribution can be seen on the right. The equation of its probability density function could be written with that extremely pleasant looking equation there. Good news, I don't think you're not going to have to use that in any of the examples or in any of your textbook exercises. It's not really a formula that you need to memorize. It's just a way of explaining, I guess, for those of you who like to see the history behind things, but that's about all it's useful for. Okay, so we have the Greek letter phi, which is a circle with your line through it, and it corresponds to the Latin letter F. So it's using a different notation, but it really is referring to like your F of, we were using F of X before, but we're going to be finding Z's as well. That's going to be a new thing coming in. When using the standard normal distribution, it is a standard practice to use Z rather than X for the standard normal distribution variable and Z rather than X for its values, so that its PDF is phi of Z. Now, my biggest reason behind that is probably going to make more sense when we do the second exercise, because we talk about Z scores. Okay, Z scores on your bell curve. So that, I believe, is why we start calling these Z in here, because it is going to correlate to Z scores later on. When looking at the standard normal distribution graph, we should note that the integral from negative infinity to infinity of whatever the curve is always going to be equal to 1. Okay, that's like what we were talking about before. Mean of the standard normal distribution will be 0. That will be the center of our data. The standard deviation will be 1. We're setting it up this way. Not all data is like this. This is just for the standard normal distribution, and we're going to manipulate data around it to make it work. A comparison of the standard normal distribution and the standard normal cumulative distribution can be seen. And we did one like this in one of our previous exercises when we graphed them, and we saw that we went from, it was a PDF, and when we integrated it, we saw that it went to the CDF curve over here. Do you remember that question? So you can see as we're integrating across, we're adding up all that area, and we would get this CDF curve happening over here. Important things to notice is when you're in the center, when you have a score of X, that would be we were talking about it before being probabilities, a probability of a half. Okay? When you get all the way to the end, that would be a probability of 1. Okay? So we come to these rules, and this is the stuff that is very, very useful. We have the empirical rule, or the 68, 95, 99.7 rule, depending on what you want to name it. When a normal distribution is standardized, it is called a standard normal distribution. The simple explanation is that the standard normal distribution, or Z distribution, is a normal distribution with a mean of 0 and a standard deviation of 1. We already said that before, but this is the cool part. In a normal distribution, the proportion of scores that are lying between 1 standard deviation of the mean is always 68%. 2 standard deviations from the mean is 95%, and 3 standard deviations from the mean is 99.7% of your data. I think there's something about this on your formula, on your NESA study sheet as well, so you don't have to memorize it, but you're probably going to use it enough that you will know these numbers. So this is a little breakdown of the 68, 95, 99.7 rule. We've got the mean and the standard deviation of 1 again, mean of 0, standard deviation of 1. The variable of a standard normal distribution is we're going to be using Z. And this is going to correlate to Z scores that can be found using X minus mu, which is our average, over the standard deviation. So in the bell curve that you see there, you can see the one standard deviation from the mean, from -1 to 1. That is your 68%. And we're going to be breaking these down into even smaller sections. You might want to only know from 0 to 1. So that's going to be the 34% here. Or on the other side, 30, symmetrical. It's beautifully symmetrical. So 34% on either side of that. If you go to -2 and +2, you have the 95%. So if you did 95% minus the 68, grab your calculators if you want to, you do 95 and you minus off the 68 and you divide that by 2, that tells you that these two little parts are 13.5 there and there. We could go a step further and find the next bit as well. If it is 99.7 for 3 standard deviations away, we would do 99.7 minus the 95, divide that by 2, and these bits in here, that one is 2.35%. Same on that side, 2.35%. What does that make the tiny little bits that are at the ends here? Because we're still not at 100% of our data. That's 99.7 though. So that means there's a 0.3 that is still both the two end bits together, which would be 0.15%, very small number, on each end. Okay, so from that, if I wanted to know what percentage of scores are between -2 and 1, I would go, let's just add together the 35%, the 34%, the 34%. I could add together the percentages that I want because I've broken it down into all these little small sections. Okay, so you might want to go into a test or an exam and you might want to draw one of those up so that you have all those percentages on there for you. Okay, however, not every score can be broken down into those sections. We might have things that are in between. Okay, so there is, it says here, there are tables on the next 4 pages which can be used to find the area under the graph for lots and lots of other numbers. Okay, there is also a note here, there are 2 points of intersection on the curve which are at the -1 and +1. So here and here, that's where the curve is inflecting, in case you want to know that. But here is our 4 pages of data. And on your test, you will be given these 4 pages of data to use. Now, there is the Z scores here. So let's maybe look at this one. There's a Z score of 0.4. Okay? We have so many different things that we could find in here. There's 3 different things we could find from that 0.4. If I had, here is my thing, not very well drawn, but there's the center. 0.4 might be about there, right? So I have 3 numbers that are next to it, that one, and that one. The first number says, what is the probability to the mean, which means it would tell me how big that space there is. So from 0 to the mean. Okay. Or second option, it says the smaller portion, which means it would tell me how big that is. I'm on the smaller side of my line. Or last option, the larger portion, it would tell me there all the way down to that end. Okay, so you're going to have to work with all 3 of those possibilities depending on the question and what it is you need to find. Okay, so pages and pages and pages of data to help you find things. Okay. Questions. Skip over the pages and pages data. Question 1. We're going to look up P of Z is less than or equal to 1 and illustrate it as an area under our phi curve. Okay. In your table, it says to look it up. So I've got a different table over here. I'm going to look up for the Z score. So these are in the Z rows, which is the first one of each one. And I need to find 1. So scrolling down. I'm getting close. There is the 1. Right there. If I wanted to know the value that would be less than 1, should I use that one, or that one? I want to go, 1 is from the center, it is slightly to the right. So if I want everything less than it, I would want the bigger portion that goes all the way down. So the one that is the bigger portion is which one? That one. Look on your chart, you've got it there. That one there is for the bigger portion. So 0.8416. So back here, the probability that Z is less than or equal to 1 is equal to 0.8413. And to illustrate that in a diagram like it asked me to, here is my bell curve. A Z score of 1, because remember 0 is in the center. The positive values are to the right, so that would be a positive 1 there. And that probability would be for everything going to the left of 1. That's what we've found. Okay, all right, so another question. Question 2. Illustrate each probability as an area under our phi curve and then calculate it using phi of 1. All of these are going to be able to be done with this 0.8413. We're going to be able to relate it back to that value that we just found. Okay, so the first one is that I want to find probability that Z is greater than or equal to 1. All right, maybe let's have a look at what that looks like. Yeah, like that. If I said greater than or equal to 1, 1 is there, it would be that section up there. Now, if this is probabilities, remember that probabilities always add to 1. Everything underneath, if I wanted the whole curve, it would all add up to 1. So I know everything to the left of the 1 is the 0.8413. So if I want the part to the right of 1, what should I do? 1 minus it. Good. So it's going to be P of Z is greater than or equal to 1. Could be found by just doing 1 minus the 0.8413 that I found in the first question. So that would be 0.1587. I mean, a lot of these things you could go back and look at your chart again and do it from there, but it is important that you learn how to manipulate your results on this bell curve. Okay, so that's what we're practicing. Okay, next one. We want the probability that Z is less than or equal to -1. So -1 would be here, and I want that part over there. It's going to be the same as the last one, yes. But let's relate it back to the original one. When you have negative values, if you had to use your chart, if you look at your chart, there are no negative Z scores on that chart. They're all the positive ones. Okay? So what you would say is the probability that Z is less than or equal to -1, it would be symmetrical. It would be the same thing as the probability of Z is greater than or equal to 1. Because I would say, all right, I need to move it over into the positive half. It's going to be the same as that part there. And that's why it's the same as that last one. It is the same as 1 minus the 0.8413, which is the 0.1587. Okay? Question C. I want the probability of a Z score between 0 and 1. Although if I use my imperial system, then I would know that already. But using my results that I've got here, 0 there, 1 there. I'm wanting that bit of space in there. I know from part 1, because we're meant to be doing all this in reference to question 1. I know that that whole bit in blue, the bit in blue there, is the 0.8413, right? That was my original question. Because it's perfectly symmetrical, this part here that I don't want would be half. Total thing is 1. It's going to be half on the left, half on the right. So I just want to subtract off 0.5. So probability that Z is between 0 and 1 would be 0.8413 minus the 0.5, minus a half, which is 0.3413. Now, as I said before, I kind of already knew that, because remember my original bell curve that I drew for you that said 68% between one standard deviation, which means when I halved that, it was 34%. 34% is 0.34. This table is just a smidgy bit more accurate, which is why it has 2 extra decimal places on it. But that 0.34 shouldn't have been surprising. Okay. Question D. I want the probability, and again, given what I just said, we already know the answer to this. Approximately 68, because I'm going between -1 and 1. That's my one space from each side of the mean. So it looks like this. And I have -1 on that side, +1 on that side, and I'm trying to find how big that space is in between them. So, given that I just worked out half of that, I could just times my last result by 2. So I'm going to say that probability that Z is between -1 and 1 is 2 lots of probability of between 0 and 1 that I found in part C. So that's 2 times 0.3413, which is 0.6826. And we can see our 68% coming out of that. Okay. So that's to give us a bit of a play with moving things around our bell curve. Let's keep going. Question 3. Explain how to find phi of 0.6 using a table and illustrate it. Okay, the 0.6 is the Z. So we are going to find in our table the probability that Z is, now when it's written in that form, that's the cumulative. We want everything up to 0.6, which means everything less than or equal to 0.6, all added up together. Okay, that's what that means. So then I'm going to go to my table. Here's my table again. And I need to find in the Z score row, I need to find 0.6. I'm too big there. 0.6 is here. There it is. And I want everything to the left. Is that going to the mean, the smaller portion, or the larger portion? Sorry, say louder. 0.6 is on that side, and I want everything less than it down there. So it's going to be the larger part. All right, so I want the larger portion, which is that one there, the 0.7257. All right, so back to here. It's a bit of backwards and forwardsing with your booklet. I'm sorry about that. We have 0.7257. And the illustration that we used, oh, that's a terrible bell curve. I'll try that again. 0 is in the middle. I want everything less than that 0.6, which was the bigger part, the bigger portion. Question 4. You ready for question 4? Not quite? Yep. No. No, it's not. It just sits slightly above. It just gets really, really close. Because technically there can be massive outliers that could be way away further. Yeah. Okay, question 4. Use symmetry and the table of values to find the probability that Z is between minus 2.1 and minus 0.4. Let's draw it first. I think that makes it easier. So 0 is in the middle. Minus 0.4 I'm going to put there. And minus 2.1 is there. And I'm trying to find that part in between them. Okay, the problem with going to my table straight away from here is, as I said before, there are no negative values in our table, only positive ones. So we use the symmetry of our bell curve. We say that area is actually going to be the same as a positive 0.4 and a positive 2.1, and that space in there. They would be identical, right? Okay, so I'm going to find the probability of a z-score less than or equal to the 2.1, but that would be everything the whole way down. If I subtracted from that the probability of a z-score that is less than 0.4, that would give me the part in between. Does that make sense? All right, I'll try an extra little line on here. When I say less than 2.1, that's giving me all of that part down there. And I'm subtracting off that part, which means I'm just getting this part in between that I want. Yes? Okay, so now we go to our chart. Back to the charts. We need to find 2.1. 2.1. And we're going all the way down to the end, which means which of the three numbers, so here's 2.1 there. Am I doing the mean, the smaller portion, or the larger portion? The larger portion, so it'll be that number, 0.9821. Then I need to find 0.4, back to 0.4, back, 0.4, there it is. And I'm going to do the larger portion of that one, which is the 0.6554. Okay? So let's write those in. Our numbers were 0.9821 minus 0.6554. And that is equal to 0.3267. Still with me? Good. Part B, we are drawing another diagram so we can visualize what's going on. We're going from minus 2.8 to 1.2. So minus 2.8 would be right down the end this way, minus 2.8. And 1.2 would be on the positive side. There, and we're after that space. Okay, first problem, we have a negative number on there. So what if we found the probability of a z-score that is between 0 and a positive 2.8, because that would give me the positive 2.8 from the middle, which is the same as the middle to the negative 2.8, symmetry, right? And then I would want to add to that the probability of the 0 to the 1.2. So I'm going to do both of these going to the mean this time, not the larger portion. Yes? There's other ways to do this. If you visualize it differently, it just means you're using different numbers, but you should end up with the same final result. Back to your tables. You guys try to tell me. So go to 2.8. Can't help myself, can I? 2.8. Look at that. Good job. Right there. Okay, so first number is, I'll say it again. I lost it. Let's say it again. 0. Good. All right, and probability from 0 to 1.2? 3, 8, 4, 9. And when you add them together, you get the answer, which is 0.8823. Yeah? Question 5. An experiment is run 1,000 times. Its random variable is the standard normal variable z. Answer these questions using the empirical rule only, which means it wants me to use the 68, 95, 99.7. So not the table. Okay. How many scores greater than 2 would you expect? Now, using our empirical form, we know that there is 95% of scores that are from -2 to 2. We can put those in square brackets for our inclusive. From -2 to 2, that's 95% of our scores. So when we have 1,000 experiments that are done here, 95% of 1,000 is 950. There is 950 scores that should be between -2 and 2. But I don't want -2 and 2. I want, let's try this. Can I do 0 and 2? What's going to be between 0 and 2? It's going to be half, right? So you're going to split that in half. So we would do 950 divided by 2. There is going to be 475 results that would be between 0 and 2. Still not quite what I'm after, but I'm working things out as I go. I was asked to find how many scores would be greater than 2. All right, greater than 2. I've got between 0 and 2. Well, might be a good time to visualize here. I know that there is 475 in there. Because there's 1,000, there would be 500 on the left-hand side of my center, 0. So if I want everything bigger than 2, I'm just going to need to do 1,000 minus the 475 minus the 500. Yes? So therefore, 1,000 minus the 500 minus the 475 means that there is 25 scores, or I could have just done 500 minus the 475, that's the same thing. 25 scores that are greater than 2. Part B. Find B if we would expect about 840 scores to be greater than B. And we have no idea what B is. But 800, we know there's 1,000 experiments. There's 1,000 experiments that we've done here. 840 is more than half, right? So whatever this is, if I want there to be 840 scores greater than it, if 0 is there, whatever this B is, it's going to have to be to the left because it's going to have to be a lot more than half of what I'm after here. 840 is above 500, more than half of what I want. Okay, so it's somewhere on that left-hand side. Okay, so if I do 840 minus the 500, that tells me that there is 340 scores that would be in that section there in red, between the B and the mean. Okay, now that 340, because this is out of 1,000, think of your 68, 95, does that 34, 340 look like anything? It's 34%. That is 34% of the 1,000, okay? So that means that it would be, should I explain that written down? Maybe I could write down from minus b to 0 equals 34%. Does that make sense? It's minus b because it's on the negative side. And that means that b would be equal to a -1. That's the value that we're after. It's one below the mean. Okay. Question 6. Deciles. What do you think a decile is? Not a, well, kind of, a tenth. So deci means that you've divided something, you've got 10. A decimeter, 10 things, all right? So a decile or decagon, 10 sides. So a decile in our normal distribution means we're dividing this into 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think I've got enough spaces there, 10. And so the first decile would be from there to there, one space. And the second would be 2 of those, 3 of those. I want 9th decile, which basically is the same as saying 0.9%. Yeah. Okay. So this is interpreted as phi is equal to 0.9. 9th decile. Okay. Small problem. I need to find what the Z is that goes with that. Find the 9th decile. I want to know the value of the Z for that. Okay, we haven't really done this yet. What we need to do is go to our table and we want to find, wait 1 second before I go to my table. Because this is going to be, if 0.9 is all the way up here, oh, it's actually, sorry, it's not the value on the end. All of 0.9 would be all of the space up to this last result here. Let me draw that neater. Let me go get rid of that. I know that up to whatever this value is here that I'm trying to find, this space in here is equal to 0.9, and I'm trying to find out what this Z value is there that goes with it. That's what I'm trying to find. Is that clearer? What did you look up? So that is the bigger portion. What I need to do when I go to my chart is I'm looking in the larger portions section and I need to find the 0.9. Now the problem is that I've got 4 decimal places here. And where's my 0.9? Still going. Oh, gone too far. 0.9, where are you? There. So we have this one and we have that one where it crosses over to 0.8 something to 0.9 something. There is no 0.9 exactly. Now we're going from the portion, we want to go back to find out what the Z score is to give us that, okay? The problem, okay, sometimes it depends on the answer. Sometimes it's, the closer one, it's pretty close to 1.28, like it's way closer than that, the other one. So some answers, they kind of just round them, but there is a way to be a little bit more precise. And I'll show you what that is, although it's still not perfect. Okay, so let's write this down. I'll write down the 2 results that we're looking at. We had phi of 1.28. That was equal to 0.8997. And the other one was phi of 1.29. It is 0.9015. So the real answer is somewhere between 1.28 and 1.29. Just depends how accurate you want to be. That's not much of a difference. Okay, so this is what we do. We want to find the difference between those two numbers that are there. So you type in your calculator and you do 0.9015 minus 0.8997. Do you get 0.0018? All right, so that's the difference between those two numbers, and ours is somewhere between them. Now I'm going to say that I'm closer to the top one. I am only 0.003, so I want 0.9. I want 0.003 more on that top one to get what I want. If I put that over the difference, 0.0018, and times it by the space between the 1.28 and the 1.29, those two numbers are going up by 0.01. Okay? That tells me a 0.001, and I think it's 66666, whatever after that. I just, 4 decimal places, our chart only does 4 decimal places, so I think 4 decimal places is enough. Okay? So I've got 0.0017 when I do that. That little tiny number there is how much I need to add on to the 1.28 to get the slightly more accurate answer. So my final Z score would be 1.28, add on that tiny little smidge that I need extra, so it's 1.2817. Now, I don't know if that's but that's how you would do it if you want a slightly more accurate result, because it's between two things. Okay, yes? Well, it is, because if you round it to 2 decimal places, it's still going to round to 1.28. It all depends on, does the question say I want this correct to however many decimal places, something like that? That would determine. It's not hugely common, but it's not impossible. It's possible. Yeah. Okay, part B. Find the third quartile, so the Q3, and the first quartile. There is a reason it's asking for the third one before the first. Why would that be? Does anyone want to guess before I tell you? Why would it say the third before the first? What's that? That's right. If we tried to find the first quartile, we're having to work with a negative Z score, which is not our preference. And given that it's symmetrical anyway, the Q3 is going to be reflected across and have the negative value for the Q1. All right, so it's nicer to work with the Q3 because it's in the positive section. All right, so to find Q3, that needs a Q of Z is going to be equal to 0.75, because I need my probability to accumulate to 0.75%. That's the cumulative part. That's not the Z score. What is the Z score that goes with that? We're going to have to go backwards through our chart again. Okay, back to the chart. 0.75. Which way am I going? That way. Down, 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 down. No, I've gone too far. Must be the other way. 0.75. So 7.4 is there. 7.5 is there. So we're between 0.67 and 0.68. We get to practice it again. Okay. All right, let's write those down. All right, I'll write them down first because then I don't have to flip the pages. So phi of 0.67 was 0.7486. 0.68 takes us to 0.7517. Okay, first thing we need to do is we need to subtract 0.7517 minus 0.7486. We need to find the difference between our two numbers there, which is 0. Yeah, what did you say, 31? 0. Yeah, you're right. Okay, now you don't always have to go to the top one. I might say this time the bottom one is 0.0017 more than what I need. So maybe I could use that one. I might go 0.0017 more, and I'm going to take this off. I'm going to go backwards a bit. I have to times that by the 0.01, which is how big the space is between my two numbers. And that gives us, I think, 0.0055. Is that right? To 4 decimal places? Okay, so the z-score is, because I was working from the bottom one, the 0.0017 came from the bottom number, I would start with the 0.7517 and I would take away the 0.0055 because I'm going backwards from the bigger one and I'm going back a little bit. So I get 0.6745. Okay, which is between 0.67 and 0.68. So it falls back in where it's supposed to go. Okay, so that is the z-score of the Q3. So let's do a little summary here. Since this curve is even, because it's even, which means symmetrical, the Q3 is the 0.6745 that I just found, and the Q1 is going to be, on the negative side, it would be negative 0.6745. It would be the same z-score, but negative because it's symmetrical. Question C. Using the interquartile range criterion, what proportion of the scores of a standard normal random variable would you expect to be outliers? Okay, it says to use interquartile range, IQR, interquartile range. Interquartile range formula is Q3 minus Q1. So our Q3 was 0.6745, and then I want to minus negative 0.6745. So the minus becomes a plus, and that's an interquartile range of 1.3490. Okay, now, an outlier. What is an outlier? Again, I'm just going to look at the positive side to begin with. The outlier formula that we learnt in year 10 was Q3 plus 1.5 times the interquartile range. That's why I had to find the interquartile range. Okay, so subbing in what I know, Q3 was 0.6745 plus 1.5 times the interquartile range, which is 1.3490. So that equals it's 2.698 or something like that. But because these are this is Z scores that I'm working, these are scores, Z scores, I might as well just round that to 2 decimal places because my chart does 2 decimal places for the Z score. 2 decimal places for the Z score, 4 decimal places if I'm going from the probability, then going back to a Z score, okay? So an outlier is going to be, so maybe the probability of an outlier, that's a good way to write it. Remember when we used that formula, we said that anything that's bigger than that would be an outlier. And because of symmetry, anything less than negative 2.7 would be an outlier on the smaller end. Okay, so I could say anything greater than 2.70 is an outlier, and I would want to add to that anything where the Z score is less than negative 2.7 would be an outlier. Now, because it's symmetrical, do I really need to work out both of them? How about I just say I want 2 lots of the greater than 2.7 one? Okay, because the little bit down that end is going to be the same as the little bit on that side. Symmetry. Use your chart. That 2.7 is the Z-score. So 2.70 Z-score. What is that as is larger than? We would want the smaller portion. So I need the 2 at the front. So it'd be 2 times 0.0035, is that what you said? Which means 0.007. Using the interquartile range criteria, what proportion? Okay, now proportion is either a fraction or a decimal. So I have found the decimal of scores that would be expected to be outliers from that data. That's it.